Hello everyone. In this video tutorial, let us discuss some of the problems related to beam design. So before starting with any problems, let us see what is laterally supported and unsupported beam. So here we given for laterally supported beam, the design bending strength is governed by yield stress, while for laterally unsupported beam, the design bending strength is governed by lateral torsional buckling. So if I take a particular beam, maybe I will take the beam section as I section. So the laterally supported condition means, so for example, this beam is embedded in a concrete slab like this. So whatever the compression flange is restrained in the horizontal direction. So in this case, so it is getting some of the strength against buckling. So if it is going to bend like this, if I apply the load, it is going to bend like this. So because of that lateral restriction, so it is not susceptible for buckling. So but in the case of laterally unsupported beam, so this is a case where it is not embedded. So if I take a same steel I section, it is not embedded in a concrete slab or anything like that. So in that case, if I apply the load, so this particular flange is going to experience a torsion or buckling. So therefore, in the first case, in the laterally supported beam, so yield stress is the governing, which will governs the bending strength. But where in the laterally unsupported beam, that torsional buckling is going to govern the bending strength. So by keeping this in mind, so as per our syllabus, so there are two types of problem will be asked. In the first type of problem, they will give the particular section, maybe ISME 400 something. They will ask us to find what is the bending moment carrying capacity of that particular beam. So that is the first type of problem. In the second type of problem, they will give particular load, either maybe UDL or maybe point load and different conditions. So based on that, we have to calculate, based on the given loading condition, we have to design the beam. So that is the second type of condition. So they will give the load, so based on that we have to design particular beam. Then we have to do the check for shear strength or a deflection or bearing capacity of the web. All those things we have to do. Also in the second type of problem, the way of asking problem may be different. They will give the room dimension, they will give the live load, dead load. So first we have to convert that into UDL. So then we have to calculate what is the shear force and bending moment. Then we have to do the design of beam. So only two types of problem. So in the first type we have to calculate what is the strength of that particular beam. In the second type, we have to design the entire beam. Then we have to do particular checks. So let us refer to the latest VT question paper. As I said, there are two types of problem will be asked. So if you see that 9B, so we have to determine the bending strength of the given section. The given particular section, by going through different steps, we have to find what is the bending strength of the given section. So in the 10th question, you can see they given all the condition, loading condition, they given room dimension, span of the beam, then they given thickness of the slab, all those things, they given live load. So by using those conditions, we have to design the beam. Then we have to do different checks. So for that reason, I have taken this particular problem. So I will read out the problem. So determine the design bending strength of ISLB 350 at 486 Newton per meter. Considering the beam to be laterally supported, the design shear force V is less than the design shear strength. The unsupported length of the beam is 3 meter. Assume steel of grade Fe 410. So this is the first type of problem. We have to find the design strength of the beam. So first step, we have to take down all the section property. So as we know, In the given data they given Fe410 steel, therefore obviously the yield strength of the steel is 250 Newton per millimeter square. You can refer the IS-800 initial pages. In the table number 1 you will get these things. So they given length of the beam 3 meter. Then for the ISLB 350, so I have the steel table here. So if you go to the steel table, so you will get all the property for ISLB 350. So by referring to that ISLB 350, I noted all these properties. These are all important. So for the design of bending moment, so we have to calculate bending moment. So these properties we have to take down. So all the values, most of the values are available in the centimeter. So you have to convert that into millimeter for the calculation purpose. So pause the video, then take down all these values. So we'll move on to the second step. So in the second step, we have to do the classification of the section. So we have the condition here. So if you go to the IS-800 page number 18, rolled section, outstanding element of compression flange. So that is nothing but flange. See the first row, we can see that B by TF value should be, for the plastic section, it should be less than 9.4 epsilon. If it is less than that, it is, I can say that plastic section. So for the web, so neutral axis at mid depth. So for the I section, we know that neutral axis at mid depth. So you can see here row number 5, D by TW value should be less than 84 epsilon. So these are the two basic condition for plastic section. So let us see what is that epsilon. Epsilon, if you come to the note, epsilon is nothing but root of 250 divided by Fy. So in the second note you can see that. So whatever the epsilon is nothing but root of 250 divided by Fy. So it is nothing but 1 in our case. So same thing we did here. So while calculating, so I have to calculate what is B by TF. So let us, what is B? So it is available in page number 19. So how to calculate B and D for the rolled section. So we have taken rolled beam here. So B is nothing but actual B divided by 2. Then we can see the D value here. So it is nothing but total depth is H. From that 2 times we have to deduct what is thickness of the flange. Same thing we did in here in this particular problem. So first we did calculated what is actual B here. So that is B, width of the flange divided by 2. So that is nothing but 165 divided by 2, 82.5. Then I calculated what is D, that is nothing but H minus 2 times thickness of the flange, that is 27.2 mm. So after that I did what is B by TF. I know that which should be less than, as per page number 18, 9.4 epsilon. We got 7.23. So therefore it is plastic section. So I can say plastic flange. So in the second condition, D by TW. So D value we calculated, what is TW, that is nothing but the thickness of the web. So we got 44.2, which is less than 84 epsilon. So I can say the entire section is plastic. So that is the first step. So next, second step. So for the laterally supported beam, so if I want to calculate what is the design bending strength, we have to refer to the page number 53. So I will move on to the IS-800, then I will go to the page number 53. Yeah, here I am referring page number 53. So before going to the clause number 8.2.1.2, so they given one condition. So D by TW value, if it is less than 67 epsilon, so no need to check for shear buckling. So in our case, you can see here D by TW value 44.2. So therefore no need to check for shear buckling. So directly I can go to the clause number 8.2.1.2. So the bending design bending strength is given by the formula MD is equal to beta B ZP into Fy divided by gamma M naught. So whatever the value we are going to get, which should be less than for the simply supported condition, so it should be 1.2 ZE Fy into gamma divided by gamma M naught. In the cantilever condition, 1.5 ZE Fy divided by gamma M naught. So for the plastic or compact section, beta B is 1. So if it is semi-compact, we have to take ZE divided by ZP. So Fi we already know, that is yield strength 250. Gamma M naught from the table 5 we can get, that is 1.1. So therefore if I come back to the problem, so beta B we taken 1. So after that we need the value of Zp. See, we already noted from the steel table what is the value of Zpz. So that is 851.11 into 10 to the power 3. Fy is 250 divided by 1.1. So we have to check for the simply supported condition, whatever the value I am going to get, we should be less than 1.2 ZE Fy gamma M naught. So also we have to note down from the steel table that what is the value of ZE. So if I substitute these values, I will get 193.43 kilonewton meter, that is the bending strength or design strength of the beam, then which is less than 205.06 kilonewton meter. So therefore I can say that it is safe. So therefore hence design bending strength of this particular beam 193.431 kilonewton meter. So by doing this we can complete this particular problem. So as I said, we have the second type of problem where we have to design the entire beam for the given loading condition. So let us see the steps involved in this particular type of problem. So first we have to note down all the data. So then we have to calculate what is the effective length. So it is nothing but a clear span plus bearing, that is nothing but thickness of the support they will give. So we already know that in the RCC, all those things, if the beam is supported on the wall like this, so clear span will be given. So if I want to find the effective span, so L plus bearing divided by 2 plus bearing divided by 2. So I taken total 1 bearing. So in that way we have to calculate what is the effective span. So then we have to calculate what is the total load, that is nothing but the total live load plus dead load. So in case if they not given what is the self weight of the beam, we can assume from 0.5 Newton per meter to 0.8 Newton per meter. So for each 1 meter, that is the load we can assume. So that is the self weight of the beam. So after adding all these things, so we have to make it as a factored load. So we have to multiply with the factor of safety 1.5. So we will get the factored load. So the second step, we have to calculate what is the bending moment and shear force. So for uniformly distributed load, we know that maximum bending moment is given by WL square by 8. Maximum shear force on the support, that is nothing but support reaction, which is given by WL by 2, WL by 2. So where L is nothing but effective length. So if I go to the point load, so the maximum bending moment is given by WL divided by 4. So we have taken here formula. So the maximum shear force is given by W by 2. So next one, third step, design of the section. So we already seen just before in the page number 53. So here we know the value of MD. So in the previous step we calculated what is the bending moment. By taking that, we have to assume, initially we have to assume we are going to design a plastic section. So we have to take beta B is equal to 1. So by doing reverse calculation, I can calculate what is the value of ZP. So once I get the value of ZP, we have to choose one section which is having more ZP value. So for example, I got 100 millimeter cube. I have to choose somewhere around 105 millimeter cube or 110 millimeter cube. So either we can refer steel table or we can refer annexure H, page number 138 of IS 800. So both the things we can refer to choose the section. So once I choose a section, we have to do 5 checks. So first check, we have to check whether it is plastic section. So we already know that from the page number 18 and 19, we can check whether it is plastic, semi-compact or buckle section. So like that 4 classification we can do by using page number 18 and page number 19. So in the problem we are going to do it in detail. So the other 4 checks we have to do. The second check we have to do for shear strength, so which is available in page number 59. So we have this particular formula. So by applying all the values, so the formula is like this: design shear strength is given by AV into FYW divided by root 3 gamma m naught. So where AV is the shear area. So we know that shear strength is taken by whatever the web. So the shear area is nothing but area of the web. So we can see here, if it is rolled section, so area of the web is given by H into TW. So if it is welded, if I take on different plates and if I made into one I section, we can see here what is the D here. By considering that as D, that is nothing but shear area. So we have to find out what is the shear strength or design shear strength, which should be greater than factored shear force. So in the first step we are going to calculate. So design shear strength should be greater than whatever the actual shear strength in our case. So the third check we have to do moment capacity. So for that, again we have to go to the page number 53. Same formula you have to use, but we have to see if I want to use that particular formula. So whatever the shear force V value should be less than design 0.6 times the design shear strength. So if it is going to be satisfied, then only I can use this particular formula. So if it is not going to satisfy that formula, so we have to go to the clause number 9.2.2, that is in page number 70. So that is the third check we have to do. So the fourth check we have to do for the check for deflection. So if you go to the page number 31, so if you refer the table number 6, so for live load and dead load conditions, so maximum deflection allowed is L by 300. So where L is the span and 300 is the factor. So actual deflection for the point load, so which is given by WL cube divided by 48 EI. So for the UDL, it is 5 by 384 WL to the power 4 divided by EI. So that is the fourth check we have to do. The final check we have to do, so that is check for web bearing. So if you go to the page number 67, so we will get this particular formula. So in that, so we will assume that the dispersion of the load in is like 1 is to 2.5. So N2 we have to calculate, that is the dispersion length. So I taken 1 is to 2.5 here, you can see here. So in the vertical direction TF plus R1, that is the height. So N2 I have to calculate. So if I do the cross multiplication, I will get this particular formula for the N2. So B1 is most of the time we are going to assume it as 80 mm. So by using this formula we have to substitute all the values. So whatever the value I am going to get, it should be greater than shear force. So let us see the first problem over here. So design a simply supported beam of a clear span 3.5 meter effectively held laterally throughout the length. That means it is a laterally supported beam. The beam is supported on wall of thickness 300 mm and carries a UDL of 10 kilonewton per meter. So let us come to the solution part. So the given load, that is 10 kilonewton per meter, bearing is 300 mm and clear span is 3.5 meter. So first we have to find what is the effective span. So already I said, if I want to find effective span, so we have to add with the bearing. So 3500 is the clear span, so I have to add the bearing, so that is 3800 mm. So self weight of the beam they not given. So as I said, if they not given in the question, we have to assume it as from 0.5 kilonewton to 0.8 kilonewton per meter. So therefore total load here is a 10.5 kilonewton per meter. So I have to make it as factored load. So I will get around 15.75. I will make it as 16 kilonewton per meter. So since it is design, I will increase little. So first, second step, we have to do what is the bending moment and shear force. They given simply supported beam. So the maximum bending moment is given by WL square by 8. So I got to 28.888 kilonewton meter. Maximum shear force, we know that WL divided by, so 2, that is nothing but support reaction. So that is 30.4 kilonewton. So the third step, so we have to design the section. So as I said, we have to refer the page number 53. Okay, so if you go to the page number 53, so we can get to this particular formula. So I will assume it as a plastic section. I will take beta b is equal to 1. So I have to find out what is the ZP value. So I know the value of moment, I know the value of Fy, and I know the value of what is gamma m naught. So by using that, I am going to calculate what is ZPZ. Okay, plastic modulus of section. So I will get it as 127 centimeter cube. So now the next step, I have to choose one section which is having ZP value more than 127 centimeter cube. So if you refer to the steel table, also you can refer, as I said, annexure H. Okay, so that also you can refer. Yeah, here we have the annexure H. So the design ZP value is required 127. I chosen here ISMB 175. Let us see here ISMB 175. So if you see the value of ZPZ, that is 166.08. So for ISMB 175, so the actual ZPZ is 166.08. So we have chosen little higher section, so it is not going to fail in the future checks. So after choosing that particular section, so I have to note down all these values from the steel table. Okay, so all the values are not available in IS-800. So again we have to go back to the steel table. So we have to note down all these values. So ZEZ also required, ZPZ also required. So one more important thing we have to refer, that is root radius. So that is R1 also we have to note. So once I choose the section, so now we have to do all the checks. So as I said, first check we have to do check for the plastic section. So in the first problem itself we have seen in the page number 18. So if it is a plastic section, so B by TF value should be less than 9.4 epsilon and D by TW value should be less than 84 epsilon. So in the page number 19, so we will get to know how we can calculate B and D value in the page number 19. So by using that, we have to do the calculation. So I got here it as it is a plastic section, so it is satisfying the condition. So first check is passed. The second check we have to do check for the shear capacity. If you go to the page number 59, so let us refer to that page number 59 in the IS-800. Yeah, here we have the formula. So first they given design strength is given by Vn divided by gamma m naught. So Vn is the nominal shear strength, gamma m naught is the factor. So Vn is given by Av into Fy divided by root 3. So by using this formula, so we know that what is AV? AV is nothing but area of the web. So for that, H into TW we have to do. In this particular figure I can say that, so this is the shear area. This is the entire shear area which is going to take shear, so that we have to calculate. So that is nothing but H into TW. So I calculated what is AB over here. Okay, so I substituted here, then Fy is 250 root 3 into 1.1 in the denominator. So the value I got 126.295 kilonewton, which is greater than whatever the shear force WL by 2. Okay, so the next check we have to do, so that is moment carrying capacity. We have to move on to the page number 53 again. So first check we have to do, so that is whatever the d by tw value which should be less than 67 epsilon, then only I can use this particular formula. Also we have to check this support reaction should be less than 0.6 times the design shear. So those condition also it is going to satisfy here. So then I can use this particular formula. So where beta B in the section classification we got it is plastic section. ZPZ value we taken from the steel table. Fy we know that 250. So I will going to substitute all these values. So I am going to get MD is 37.7 into 10 to the power 6. So also I have to check for the simply supported condition. So whatever the value we are going to get here, which should be less than 1.2 ZeFi gamma m naught. So both the condition it is going to satisfy. So therefore whatever our design, that is safe, because design shear strength of our beam which is greater than 28.8 kilonewton meter. So that is the WL square by 8 value in our case. So this is also safe in moment carrying capacity. So the next check we have to do, that is check for deflection. So if you go to the page number 31, yeah, so in this particular page, so we are not going to consider industrial building. In the other building, so vertical load we have considered. So whatever the UDL they given, so that is vertical load. So try to refer your particular IS-800. So go to the page number 31. So you can refer this particular table. So in that other buildings, so floor and roof load is going to come into picture. So element is not susceptible to cracking. So one more is element is susceptible to cracking. So I'm going to take the first condition, element not susceptible to cracking. So because RCC beam or slab you are going to use, it is not susceptible to cracking. So therefore span by constant is nothing but 300. Okay, so that condition I'm going to take here. So therefore in the check for deflection page number 31 table 6, so allowable deflection L by 300. So we have to calculate what is actual deflection. We know the formula, actual deflection for the UDL simply supported beam with the UDL. So that is 5 by 384 WL to the power 4 divided by EIZZ. So all the values I am going to substitute here in millimeter. So because E value I can substitute, that is 2 into 10 to the power 5 for steel. Then IZZ, so we noted the value of I from the steel table in the beginning of this particular problem. So we noted what is the I value from the steel table. So that we are going to substitute here. Okay, so whatever the maximum I value, that we are going to substitute here. I have IXX and IYY. So in that IXX is maximum, that I am going to substitute here. So but while substituting it should be in millimeter. So by substituting all the values we are going to get actual deflection is 10.67. So allowable deflection, if I do 3800 divided by 300, I am going to get 12.67 mm. So therefore Actual deflection is less than allowable deflection, so therefore this is safe in deflection. So I have chosen little higher section. If you see the ZP value, so this is the reason. So if I am not choosing higher value, so it is going to fail. We have to do the redesign. So if I come to the last part, that is check for web bearing. So if I come to the last part, so we have to refer page number 67. So in the page number 67, we are going to get this particular formula. Okay, B1 N2 TW into Fy divided by gamma m naught. So by taking that formula, so I said B1 we are going to assume 80 mm for I section or most of the rolled section, and N2 we have to calculate. So N2, the load dispersion in the ratio of 1 is to 2.5, horizontally 2.5, vertically 1. So by doing the cross multiplication, you can see here I calculate in the vertical 1, horizontal 2.5. So vertical here is TF plus R1. So that is the root radius we already noted. Horizontal it is N2. If I do the cross multiplication, N2 is nothing but 2.5 into TF plus R1. So I got the N2 value is 46.5. So I will substitute all the things in this particular equation. So TW is the thickness of the web, Fy is 250, gamma m naught is 1.1. I will get 158.125, so which is much greater than 30.4 kilonewton. This is nothing but shear force. So therefore our section is safe in web bearing. Okay, so all the 5 checks we have done, so it is going to pass in all the 5 checks. So therefore we can provide whatever the design section we have taken. So as I said, design problem can be asked in the second type. So we are going to do that now. So let us see how they are going to ask. A roof hall measuring 8 meter into 12 meter consisting of 100 mm RCC slab supported on steel I-beam, spaces 3 meter apart, that is 3 meters center to center, as shown in the figure. The finishing load may be taken as 1.5 kilonewton per meter square and live load as again 1.5 kilonewton per meter square. Take wall thickness as 300 mm. Design the steel beam. So this is the laterally supported condition because they give an RCC slab. Okay, so let us come to the solution part. So first step we have to do the load calculation. So in the previous case they directly given one UDL. So in the previous problem, so they given UDL, so directly we can calculate what is bending moment and shear force. But here we cannot do that. So we have to first find what is the UDL is going to act. So for that, so let us do what is the weight of the RCC slab. So if I want to find the weight, so I want to find it as a UDL. So therefore I have to do density into thickness into slab width. So if I see that I am going to design this particular beam. Okay, so load coming from this particular panel and from this particular panel load is going to come on that particular beam. So load coming is half whatever the load on here, that is going to come on this particular beam. So half of the load from this panel is going to come on this particular beam. So therefore I can say that 1.5 meter of this panel and 1.5 meter of this panel is going to come to that particular beam. So therefore I am going to multiply with the 3 meters. So if I see that total it is 3 meter slab is going to rest on that particular beam. So therefore if I see that kilonewton per meter cube, that is the density, thickness in meter and width is in meter, so I'm going to get the value in kilonewton per meter. So therefore weight of the RCC slab 25.1, they given 100 mm thickness, then 3 is the load, total load is going to coming to on that particular panel. Okay, so that is the first load is going to come. Then finishing load, they given it as 1.5 kilonewton per meter square in the question finishing load. So again I can see that whatever the finishing load on coming on this particular beam, so whatever acting on this particular portion, so therefore 1.5 into 3 meter I have to do, so it is 4.5 kilonewton per meter. So the finishing load they given in kilonewton per meter square, if I multiply with meter, so I will get kilonewton per meter. So the self weight of the beam they not given. So I said in the previous part of this video, we have to assume in between 0.5 kilonewton per meter to 0.8 kilonewton meter. So I kilonewton per meter. So I assumed here 0.8 kilonewton per meter. So therefore the total dead load I am going to get here, if I add all three values, 12.8 kilonewton per meter. So next thing we have to take live load. So again they given in the question live load is 1.5 kilonewton per meter square. So I will multiply with 3 meter. So that is the span which is going to rest on the beam. So therefore again 4.5 kilonewton per meter is the live load. So therefore total load we are going to get dead load, live load plus dead load, that is 17.3 kilonewton per meter. Therefore factored load we have to multiply with the 1.5, so that is 25.95 kilonewton per. So I will move on to the next step. So calculation of bending moment and shear force. So maximum bending moment, we can see here it is simply supported condition. So therefore first we have to find effective span. So if you see in the problem, the length of the beam here it is 8 meter. So in this way we are going to design the beam, so 8 meter. So effective span I have to calculate first. So we have to add the bearing. So therefore effective span is 8.3 meter. So maximum bending moment for simply supported condition WL square by 8. So I will get to 223.46 kilonewton meter. Design shear strength WL divided by 2, 107.69 kilonewton. So the next step, design of member. So we have to refer page number 53. So you can go to the IS-800, go to the page number 53. So first I have to assume it as a plastic section. So later I'm going to check whether it is plastic. So if it is plastic section, beta B is equal to 1. So by taking that condition, I'm going to calculate what is the ZP value. So ZP I'm going to get here 983,224, that is 9,83,224 millimeter cube. So first I am going to convert that into centimeter cube. So I am going to refer the steel table or annexure H of IS-800 page 138, you can refer. So I have to choose one section which is having more ZP value. So I chosen here section ISMB 400. So you can refer that one. So for ISMB 400, Z value is 1176.18 centimeter cube. So also note down what is ZEZ value. It is required later. Okay. So after taking that section, note on all the properties. So main properties required are these, that is H, B, thickness of the flange, thickness of the web, then root radius is required, IXX and IYY is required. So if you note down maximum I value, that is also fine. Then the next check, so that is check number 1 we have to do, that is check for plastic section. So if you refer page number 18 and 19, I said for the plastic section B by TF value should be less than 9.4 epsilon and D by TW value should be less than 84 epsilon. So refer the steel table page number 19 and 18. So you can classify the section over there. In the page number 18, you can get outstanding element of compression flange row for the rolled section B by TF should be less than 9.4 epsilon, first row. And in the fifth row for the web we are going to get neutral axis at mid depth. For the I section, neutral axis at mid depth, therefore D by TW should be less than 84 epsilon. So what is B and D, you can calculate from page number 18. You can refer this particular figure, so you can find out. So B is nothing but width of the flange divided by 2, D is nothing but the H minus 2 times TF you have to do. So I'm going to get B is 70, 140 divided by 2, D is 380, 368. So epsilon we know that root of 250 divided by Fy, so you'll get 1. So in the both the condition it is going to satisfy the plastic section condition, so it is safe. So they check for shear. So from the page number 59, yes, design shear strength is given by Vd is equal to Vn divided by gamma m naught, where AB is the area of the shear area. I can say shear area, that is nothing but area of the web. So that is given by H into Tw. So I can get that value 400 into 8.9 into 250 divided by root 3 into 1.1 in the denominator. So design shear strength is 467.128, which is greater than actual shear. So what we calculated, that is 107.69, therefore it is safe. So the next check we have to do, check for the moment capacity. So before checking for the moment capacity, if you go to the page number 53, so in that first check, if I want to use that particular formula, so I have to check for this condition. So if you go to the page number 53, you can see that particular formula. So if it is going to satisfy, then only I can use this particular equation. In the clause number 8.2.1, they give one. So whatever the shear should be less than 0.6 Vd. So Vd is the design shear. So here we can check it is going to satisfy. Okay, so 0.6 Vd is 280.27, which is much greater than 107.61. So therefore I can use this particular formula, beta b z p into Fy gamma m naught. So in the previous first check I checked for the classification, we got it as plastic section, so therefore I can use beta b is equal to 1. So Zp we noted from the steel table, I can substitute that. So I will get Md is 267.31 into 10 to the power 6. So also we have to check which should be less than 1.2 ZeFy divided by gamma m naught. So for from this same page, in the page number 53, so for the simply supported and cantilever condition they given. So for cantilever 1.5 ZeFy gamma m naught. So that is I'm going to get to 278.18 into 10 to the power 6. So you have to see Ze. So we have to substitute Z value of what we calculated from the steel table. So it is going to satisfy. So the last two checks we have to do. So one is for deflection. So we already referred page number 31, table 6. So span uh, divided by 300, that is the actual deflection. So you can refer that page table 6. So actual deflection 5 by 384 WL to the power 4 divided by E into IXX. So where W is the working load, we have to substitute here. So all the values should be in millimeter. So whatever the actual deflection, we are going to get 26.127, which is less than maximum deflection, that is 8300 divided by 300. So again E value we already know, that is 2 into 10 to the power 5 for steel. So the last check we have to do, so check for web bearing in the page number 67. So if you refer that particular page, you will get this particular formula. So we are going to assume B1 is equal to 80 mm. So load dispersion in the form of 1 is to 2.5. By using that we have taken N2 is equal to 2.5 into Tf plus R1, that is R1 is the root radius. Substitute all the values, we are going to get 313.52 kilonewton, which is much greater than shear force. Therefore it is safe in web bearing.